4 already?
Yes, sir.
Oh, we did. 10? Let me talk a little bit about homework 4. So we have a sort of a plan for today. So we talk about homework 4. And then Keishan's going to do some demos about that. We'll see how long that takes. We may not stay until 4:30 here. And then I want to talk about something that's a little bit more complex. Let's call it graphical models. That's the same as saying Bayesian networks. And there's some other names on it. So that would be something that we don't actually do, but will be the natural continuation of this track of generative models. So after we see the basic one, naive Bayes, GDA, and in the homework we have there one particular important item. It's a mixture of non-Gaussian distributions. So you have a problem, something with flipping a bunch of coins. That's a mixture of Bernoulli or binomial distributions. That's kind of the plan for today, and that's the last lecture about generative models. Starting next week, we're going to move on to completely something else. Okay, something to do with boosting algorithms. We're done with statistics. Okay, we're not quite done, but we're done on this track. Right? So. First thing that I want to talk about homework 4 is you have a naive Bayes problem, right? Remember? I don't know if you have looked at it. So something that says, so let me start in here. What do we have? We have probability of y given x is probability of x given y times probability of y divided by normalization. That's our base equation. That's the fundamental of all generative models. Because what we want for prediction is this. That's my classifier. Give me the class for a patient or email. This is the email, that's the class. And this is what I estimate from data. From data, I estimate the distribution of patients in a given class. Right? So now with naive Bayes, so this is our training. And if we do naive Bayes, we say P of x given y is P of x is actually x1, x2, up to xd, right? That's an x given y. So we say that is P of x1 given y times P of x2 given y times P of xd given y. Since we're doing this per class, y is not important here. Given y means I do it for the red class and for the blue class and for the green class separately, right? So I'm going to have to do all this for the, if you have span base, this will be for the positive classes one way and the negative class. Now, my question is, what is this? This is a unidimensional variable, right? So we're going to say here one dimension. Given the class again doesn't matter because I'm doing for that particular class. So I have two options in naive Bayes here. How do I estimate P of x, which I'm going to say unidimensional, to make it clear, in a given class, in class y equals 0, for example. That is, I'm going to take all the points that have y equals 0, and I'm going to estimate the frequencies of these particular values, right? So that comes down to estimate distribution of values x1. This is from I equal 1 to n, all the data points. Like I said, I still look at all the data points, but I'm looking at just one column of the data. For all restricted to yi equals 0. So I'm only looking at the data points that have that particular class. So again, if I look at the feature matrix, I'm going to say, okay, first select only the labels that have y equals 0 from the matrix, and then look at that particular column, which is this column 1. This is a D, this is column D. So these would be the values that interest me here. Inside that class y equals 0, how do things are distributed? So how can I do this? I can fit a curve like before, right? I can take those values and feed them through a Gaussian or whatever distribution I like. So I have two options. I can fit unidimensional curve for p of xi given y equals 0, like a Gaussian or an exponential or some other distribution that I like. Or, because this is a unidimensional distribution, I have the option of doing the brute force, which I don't have in multidimension. In multidimension, there will be too many possibilities to try to count the data. So I'm going to say here, I can do this brute force, aka count data, and make that into frequencies. So I think the homework asks for both things. Ask you to do it first, brute force, like count the data. This is the same as creating a histogram. All these names mean the same thing. Creating a histogram, counting the data, or brute force. Again, we can't do this in multidimensional spaces. There are too many cells there to count all of them. We don't have enough data to cover all these cells, but even if we would, it'd be computationally impossible. But in here we do, we are able to do that, right? I literally, what do I mean by that? Well, I take all these values here, and I'm looking at, this is the values of interest. The values become a range from mean to max, right? And I can put all these values I see, those values become dots in here. Whenever I see a value, maybe some parts are very frequent and some parts are less frequent, right? And then in here I want to measure their frequencies. So a histogram, I think most of you have seen what the histogram is, right? I'm bucketizing the thing. And in a first sense, in this bullet sense, fitting a curve will be pick the curve you want to fit, say a Gaussian, and just fit the best Gaussian you can in there. That is computing from data the mean and variance. Every curve fitting comes down to computing the curve parameters. Right? To fit a curve, it's equivalent with compute curve parameters. If it's a Gaussian, it's a mu and sigma. If it's a Poisson distribution, it's a lambda, so on and so forth. Whatever those coefficients are. I want to talk more about this. This is easier, right? Brute force. If I have no better idea, I can split this thing into a bunch of intervals. Does the homework say how many intervals to split? 4, 3, 4. So if somebody tells me 4, but in practice nobody tells me how many, but let's say somebody tells me it's 4. I say, okay, take the min and max, maybe. Here's the 4 buckets, right? Let's call this bucket 1, bucket 2, bucket 3, and bucket 4. And then I count how many values have I seen in each bucket. So then I put some bars. This is that many, this is fewer, this is even fewer, and this is nothing in here, apparently. This is a small line. And I can make these counts now into a distribution by dividing by the total. Right? That's a brute force counting. Now, I make a small parenthesis here. My experience as a data scientist, more or less into the consulting, where it's actual problems. You know, the biggest difference between research or consulting, research in academia and consulting or industry side, is that in industry you gotta make things work. Just beautiful papers with theory are not cutting it, right? You just gotta make the damn thing work. So people in industry, whatever they say, they don't care so much about the theory if the actual program doesn't work, right? So there's a difference there. And I can tell you the first thing I do on any data, no matter what the customer wants, is to run naive Bayes and decision trees. Because naive Bayes and decision trees will tell me something about the data right away. What's up in here? If naive Bayes works reasonably well, I can presume that there's reasonable independence, right? This is the independence assumption between the features. And can this be screwed up massively? Can I come up with an example where this independence makes things terrible? Yes, I can. Can you? Where this independence, if I'm asking in practice, give me an example of some sort of data where this independence will cause a lot of trouble. Yes.
Text like a normal sentence or something.
What?
A sentence. If that's our data point like a sentence, we're trying to classify a sentence or something like it's a good or bad, something like that. Then each words are like connected. A word which is used in our sentence.
Right. So what he's pointing out is that these in sentences or text may not satisfy the independence, right? What I'm saying is, even this theoretically, that's true. This is not necessarily a reason, a guarantee that's not going to work in practice, right? Like, what this model says, if you have independence, this is going to work. What he's saying, I give an example when you don't have independence. We can all agree with that. But that doesn't mean the model won't do the predictions necessarily, right? The fact that there's a guarantee for independent case doesn't mean necessarily it won't work when you don't have independence. So my question is, can you show me an example where this is definitely not going to work? Why it wouldn't work?
Because some of the features are 0.
Oh yeah, so that's not what I'm asking for. He's asking a different question, which I was about to ask. What do I do here? So that's a different problem. If I do brute force and I get no data, I get a 0. 0 is a very, very bad thing in probabilities. You want to avoid that at all costs. Same thing with the covariance matrix. Every time you get a 0 on a diagonal of a covariance, you want to stop and do something before you move on. Because it's just no good for math. But that's a different question. I want to say, can somebody construct an artificial example somehow where if I use naive Bayes, it won't work?
Images, we can consider each pixel as a word, but in words, naive Bayes works very well. But you can't make the same assumption in images because the pixels matter. Like where, so if you're talking about a cat, where one pixel is with respect to other pixel, that matters. Right? So you can't make that independent. I mean, even if you make it, it won't work well.
I think your example is the same like his. It's speculative. Say, I don't think it's going to work because I have dependencies in there, right? And that kind of, maybe you're right. But again, there's no guarantee naive Bayes won't work.
If you have multiple features which are exactly the same always, like 100% correlated, then you would have like X1.
I take a small data set like the wine data set with 10 features. I pick one of them that's not very good. It's not the one feature that determines the outcome, right? And what do I do with that one? I duplicate it 1,000 times. So again, what do? I pick a data set like the wine data set that has 12 features. Reasonably small number. You can get high accuracy on a wine data set, right? Or reasonably high. How much people have got?
100%.
Right. So then what happens if I take one feature that's not a very good feature? So that feature alone can't give me more than 60%, right? It's some correlation, but it's not. And I duplicate it, literally duplicate that column many, many, many times. My claim is that what naive Bayes is going to do, that's the only feature that's going to matter in the end. Because it does a product of things. And the other features are 10 out of now 1,000 features. So this feature that got duplicated is going to completely overwhelm the other ones.
Is it no longer independent? I mean, you now have like complete dependence between 1,000 features.
Right, right. So I get the dependence that's going to break this model. Would that, the same thing, break regression if I take one feature like that that's not very good and I duplicate it 1,000 times? Would I break regression that way?
It will not. No, because it will change by constant. The weights will become 0 for each of them.
Regression will control the weights, right? But here there's no weights. It's just multiplicative of this product. So if I have 1,000 of them that are the same, they're going to overwhelm the other 9 features that somehow matter. Okay? So that's a typical way to screw up a naive Bayes that works, to get one feature and duplicate it many, many, many times. However, data sets are very unlikely to look like this. This is a very artificial example constructed by hand. In reality, naive Bayes can tell us a lot of things about the data, even though there's no guarantee of independence. So that's what I'm saying. Naive Bayes is a good thing to run. Same thing with the decision tree. If you look at the decision tree at the top of the splits, you get to learn really quickly what features to look at. So that's my parenthesis. Now back to this brute force. My other question that I had in mind is, if I do brute force, first of all, if I fit a curve, do I have the zero problem? Do I have to worry about zeros?
No.
No, because fitting a curve, again, comes down to estimating parameters. So suppose I want to fit a Gaussian. That's not really a Gaussian. But suppose I want to fit this one. I have to compute mean and variance, right? And I'm going to compute mean and variance from data. Variance is typically, there's some estimator there, 1 divided by n minus 1, scattered matrix, right? Mean is the mean, I'm that. But with the zero problem, if I do brute force, what should I do?
Shift some mass from B1 to B4, or all of them. Take some constant mass from all of them and then shift it to the end.
Okay, so we need to do something here. Let's call that smoothing. And let's think about, I don't know about shifting some mass. It may be what I'm trying to do here, maybe not. Let's see. So there's 2 smoothing ideas that, so first of all, you have to be aware of the problem. When you estimate frequencies directly from data, you're going to have this problem. That's required in here in all data classes. You have to be aware of this problem. And I'm going to require that you know at least 2 smoothing techniques that are very, very easy. So you don't go into anything complicated. But you should be aware that smoothing in itself, it's a subfield of statistics. It's a lot of theory that can go into how to smooth data. So the ones that I have in mind, what is this estimator here? This brute force estimator is probability of x, a particular x becomes what? So this is saying probability of an x is the count in x bucket. Right? It's how many things like x I have there. It's how many things fit in that bucket divided by the total count. That is the brute force estimate. Let's just say that's for notation c divided by cx divided by n. So one smoothing idea is to say, how about I say from here changes to cx plus 1 divided by n plus the number of buckets. So number of buckets in here is 4. Because I picked 4. Yes.
Sir, I missed that part. What's smoothing for? Why do we use smoothing?
So 4 is given by the problem. We can use typical histograms, default value is 10, I believe. And MATLAB, for example, has a way to intelligently detect how many buckets you want for a certain data set. Measure some variance and say that's how many buckets you need. Smoothing has to do, one of the problems of smoothing is this 0 value. I may, even if I choose 4 buckets or 10 buckets, I may have some buckets with no data in them. But brute force estimate in that case would be count divided by the total, that's 0. So what do I do? One option is to do this. So I take my frequencies as they come, divide by n, but I add to the all numerators 1 and to all denominators the number of buckets. Now this is a valid distribution, right? Meaning the sum sums to 1 because the sum of the numerators sum to n. Is this a valid distribution?
Yes.
Yeah, because the sum of the numerators will be, sum of Cx will be n, right? And how many buckets I have? B buckets. So how many ones I have there? 1 plus 1 plus 1 plus 1, that will be B, so the total will be n, right? So if this is a valid distribution over buckets, then this is valid distribution. Because the sum will be 1. This is called Laplace smoothing. And there is an entire theory of how to get to this value. It's a pretty easy one to implement, of course. I think we can generalize this Laplace smoothing to say, how about I want to control Cx plus epsilon divided by n plus, what do I need here? I need to sum to 1, right? When I
Number
sum
of buckets
to
into epsilon.
I need number of buckets times epsilon, right? That's what I need. So instead of 1, I add an epsilon now. It's still kind of Laplace smoothing, same idea. What's the effect of this with an epsilon small?
Smooth very little.
Smooth very little. Smooth, a small effect. In other words, I'm pretty close to the raw estimates, right? What's the effect with the big epsilon?
So you have a large effect.
Smoothing has a large effect. This corresponds to what kind of prior, but I want to talk about that in a second. I think if I put epsilon big, I'm effectively creating a strong prior.
The form distribution.
Right, so this is a strong prior. Prior being absent of evidence. So if I have no trials, this is n is the number of data points or observations, right? If I have no observation, n is 0. Cx it's also 0, right? Because if I have no observation, I have no count. The prior will be epsilon divided by b epsilon. That is 1 over b. Now that prior is also the case. Both cases have the same prior. The prior at n equals 0 is epsilon divided by b epsilon, so that is 1 over number of buckets, which is uniform, right? But this is a strong prior, and this is a weak prior. What's the difference between those? Weak prior versus strong prior have to do with how much data you want to see before you start changing your mind from the prior. So both these ideas say, in absence of any evidence, the sign probability is 1 over number of buckets. If I haven't seen no data. This one will change quickly once I start seeing data. Weak prior means the probability of X changes quickly as n increases. This P of X changes slowly as n increases. So you have another problem in the homework that's related to this concept, the one that you asked out of this hours yesterday. That one said that you have a coin that it's either a fake coin or a double-headed coin, right? And f by f plus 1, what's given there, is your prior that you are given a correct coin, a fair coin. So if f is 1, your prior will be 1/2 in that problem, because f divided by f plus 1 will be 1/2, which means your prior belief, without seeing the coin, is that a coin at random has 50-50 chance of being fair versus double-headed. That's very unlikely, right? If somebody gives you a coin, your prior is not going to be 50-50. most people would assume a coin is fair with a very high probability, right? So that F in reality, in practice, would be more like 99%. Would be 99 by 100. That is a correct, fair coin. So this is a very important problem, very important issue in Bayesian, Bayesian, all kind of inferences. This has to do with this right here, right? So these priors, you don't want to start from just raw estimates. Like I said, there's a zero problem, but there's also other problems in there. Even if I don't have zero, suppose I have a 1, these estimates are unreliable if they are very few trials, very few dots in there, right? Think about a coin. If I flip a coin 3 times, what are the possibilities? Splits between heads and tails. It's either 3-0 or 2-1. That's the only option, right? 3-0 or 2-1. I mean, or 1-2. Either way, if I lose raw counts, I'm going to get what? In a 3-0 case, I'm going to get 100% heads. That's wrong. And if I get 2-1, I'm going to get 66% versus 33%, right? But in reality, what's the problem here? I can't estimate the probability of this coin being heads, even if it's not 50-50. I can't estimate it because I don't have enough data, right? 3 trials is not enough to estimate the bias of the coin. So the general problem with sampling is not just zero, is that some buckets have very little data, they are not reliable estimates. That's why we use a prior. When you use a prior, it's easy to determine what prior to use. So in a coin, you would use a prior that the coin is fair, probably. That's the most typical case. You have a probability on the coin being fair. The difficult part in data problems is this. How strong the prior should be. It's not what is the prior, whether it's uniform or something else. It's how strong do I want to make the prior. That has to do with how much evidence do I require to change my mind. If it's too weak, means I'm going to change my mind very quickly and I'm back to the 3-0 to 1. Whatever I do, I'm going to get a weird probability. If it changes, if the prior is too strong, I'm changing my mind too slowly, I'm requiring a lot of data before I start believing something else than the prior. So problem who do risk assessments, think about you're a bank. Customer comes in, says, I'm good, I'm young, I got a job, I need $1 million loan for my house. You are the banker now. You look at the guy, he has the papers, he has a job, he's young, okay? You need to have a prior here, right? You can't give $1 million to anybody who walks in the door, right? You're gonna have some prior. But that prior, if it's too weak, you're gonna give the $1 million too fast, just looking at the papers. If it's too strong, you're gonna require too much paperwork and too much evidence before you give the loan. So any risk assessment process, like a bank or insurance company or even a hospital, or anything that has to do with risk, will have to have the proper prior to fit in order to make good of the business. In fact, a lot of financial crises can be shown are controlled by priors. Like the 2008 big crisis, people had weak priors. Anybody who come in the door, they would get a loan. And that way, eventually too many bad loans were issued. I don't know exactly the economy of what kind of loans, but it's that kind of problem that happened. Okay, so that's one thing that we can do. And this is an actual generalization of it that controls the strength of the prior. What's another thing that we can do? A foreground, background, smoothing. In foreground background smoothing, I'm going to compute this raw probability in 2 ways. So for the foreground, I have the P, let's call it foreground of X. It's the count bucket divided by the total. And I want to do kind of the same thing in the background. So how do I compute this background? It's still divided by the total. So this is, and still a count in a bucket. But I want to expand this to a larger scope. So I'm going to give you an example, and you kind of have to figure out for me what do I mean. I mean to say, I have a problem, say in text, and I'm trying to estimate what words are important for a topic. Say, what's the current topic being discussed right now? Building a wall at the border of Mexico or something like this, right? I want to know, okay, I want to estimate the frequencies of the words that have to do with that thing. So I applied my schema here, right? I said, okay, Y class, it's all the tweets or all the text or all the articles that have to do with the border wall. So I restrict my estimated for those things that are relevant, right? And I say within this scope, I can measure frequencies, right? I can say, look at all these articles that talk about the border wall, or articles that have been deemed interesting by some people. Whoever read an article can mark it, this is a good article about that. And then I look at these frequencies. I have all the words in English language, and I count, okay, how many times each word appear in those articles. And articles that appear a lot, I'm going to say those, words that appear a lot in those articles are important words, and words that are not appear are not important words. I can measure their frequencies. That would be my foreground probability for those words. So in here, X in this example would be a word, right? I measure the frequencies of words related to a particular topic that I have in mind. In this case, the border wall. Now, how do I get the background probability? That's the same, that's of the same X. So it's still on the words. But how do I make a bigger scope of it? Yes?
Is it you expand things you're looking at everything? So you want to see how much this is relative to like all the articles in general.
Right. I expand the scope. Background probability is not focused on the topic I'm looking at right now, aka the border wall. I can look at all the articles, or maybe all the popular articles, or maybe everything that has been written since the border wall discussion started a year ago, or 2 years, I don't even know. Took all these articles, in not just the border wall ones, and measured the probability of words in those articles. Now, these probabilities won't be related, right, directly to the border wall, because I'm measuring hundreds of thousands of articles. It will be more like a general probability of seeing certain words in English language or in articles. It won't be related to the wall. So if we take this whole example and we make it general, what is the difference between this and this? So the procedure is the same. Count in a bucket, divide by the total. But this is for a class fixed. And this is for all classes. So this is a general probability of seeing those values in data, not for a specific class. So this works when, typically this works. So the overall probability that I'm going to have is some lambda times pf of x plus 1 minus lambda pb of x. So that's going to be with lambda a parameter between 0 and 1. So that's a foreground, background kind of approximation that says, I'm going to first create a general probability of feature values in all data. That's my prior. And I'm going to apply that prior to the raw estimate in a linear fashion. Now, it doesn't have to be linear, right? I can come up with all kinds of combinations that overall would give me a density function or a probability distribution. it's easy to see why this is a density function. If you combine linearly two densities with coefficients that sum to 1, it's like in the mixture that we talked about. You're going to get a density, right? But it's not the only way to create a probability out of this. Obviously, if lambda is very high, very close to 1, I'm sticking more to the raw probabilities. And if lambda is very small, I'm sticking with a strong prior, and I'm not changing the prior that much, right? This is the evidence. And this is prior. This is a lot used for text. This mechanism, it's very popular for text. Any statistical method that processes frequency from text, like words or bigrams or whatever it's that I'm looking in text to see, this is a typical way to smooth probabilities for text. Now, one more thing about this. When does this work very well? Would it work for, say, spam data set? What was the proportion of spam versus not spam in there? 30 to 70, say. Let's just assume it's 30 to 70 or 40, 60. Would that be the kind of thing that works very well? I mean, again, when this works very well is if I don't have enough data to use, in any estimation problem, if I have enough data, I want to use the raw counts directly. So when I don't have enough data for a class, but I do have enough data for all classes. When is that? I would say that's not typically a problem like the spam-based data set. Somebody else. Make a guess. When would I have this problem? For a particular class, 6 can be very sparse. I may not have enough data to do this. But in general, if I use all classes, I have enough data. I mean, the way I put it, I think it's kind of clear. Yes?
The stock market example that you gave in the previous lecture, you can't predict outcomes that you haven't seen or that are like very rare.
That's too extreme. That you can't predict anything in there. Whether you do smoothing or not, machine learning is going to go crazy in those instances. Somebody else.
If you're building a movie recommendation for a user, so a set of all the movies that are released till now will be large, but a user may like only a subset,
Right.
a very small subset of all the movies.
That's a good example. But in general, it has to do when each class or some classes are relatively small. And his example is very good in that sense. A user doesn't see that many movies, right? It sees only a few movies. But the number of movies that are being watched overall is very large, right? So if you look at all movies, you get a pretty good sense of prior, say for sentiment analysis, what words are good and what words are bad or whatever it is that you want to predict. But look at somebody, my movies, I watched 3 movies in the last 2 years. So from my personal experience, it's very hard. I wrote no review, I only wrote a sentence, what a waste of time. From that single thing, you can't estimate a prior of words, right? It's just not enough. But if you look at what everyone writes, you can estimate pretty easily what words mean for movies. So in general, when some classes are relatively small and sparse, but overall you have enough data, this is a good strategy. So that's what I'm saying. For spam-based, it may not be, because for spam-based, you don't estimate much better from the whole set than you estimate from one class.
Does that mean this will work pretty well for anomaly detection?
I don't know. Anomalies are a problem for machine learning in general, because if I have an anomaly, I have to be able to detect it's an anomaly, as in there can't be enough. This is more like a philosophical answer. If there's enough anomalies like that one, it's not an anomaly anymore, sort of thing, right? Once I see enough points like the anomaly, that's when machine learning starts working. Then it's not an anomaly. If I can, so I'm not sure what you have in mind. You probably have something exact in mind what you mean by anomaly detection.
Yeah, I mean, like if we have 2 classes, say not an anomaly and an anomaly, where the anomaly class has got very less data, but the not anomaly have I've got a lot of plenty of data for not an anomaly case.
So if I think that's true, but I wouldn't use that. So what he's saying is, how do I know it's an anomaly? An anomaly is something that's isolated, right? By definition, it's something that has no values around. I would say for anomaly, the best thing to do is something that we didn't do yet, but we will. Something like nearest neighbors. Nearest neighbors compute the distance between the points. We haven't done that yet, but I think most of you have heard of that technique, right? And I look at the distance and I say, okay, I can compute based on that distance what kind of neighborhood I have around the point. Like how many points are around there. Every time I see a neighborhood that's empty, just that point, that pretty much is an anomaly. Yes?
So let's say my foreground, I have very small amount of data points. Then should I take bigger lambda value or smaller lambda value?
That's a good question. In information retrieval, they play a lot with how to compute the lambdas adaptively or not. So whether you want to have a fixed lambda, or you want to change lambda based on distribution of words, vocabulary sizes, so on and so forth. So if you go into NLP and into information retrieval, you have a very specific treatment of these lambdas, how to combine those things. But I think that's not important for us right now. I want you guys to, I'm going to move on, to remember three things here, very important. One, zeros and sparse data, it's a big problem for estimating frequency directly from data. If you don't know what you do, you're much better off fitting a curve. Trying to estimate frequencies for small data, like I gave the example of flip a coin 3 times, give me the bias of the coin. You cannot get the bias right from 3 flips. No matter how the flips come, 3, 0 to 1, the estimate is going to be incorrect. Right? If you do brute force counting, because you do it for most of the classes, but for some class in particular you don't have enough data, you should be aware of 2 smoothing techniques. One that controls the numerator denominator prior this way. Strong epsilon means a strong prior, heavy epsilon. A weak epsilon means pretty much close to row count. Or this foreground background idea that I can compute something in general, and then for each class have its own distribution and mix it in a linear fashion.
Epsilon, high and low would depend on the domain, right?
You'd have to do some trial error or treat it as a hyperparameter to see how that works. It's hard to guess an epsilon in advance. Laplace says uniform 1 over b, but uniform, it's any epsilon divided by b epsilon. It's just how strong you want the prior to be. Yes.
So when we fit a curve, if you have like small amount of data, is it, so we do that, that is like standard distribution, Gaussian distribution?
So you make an assumption based on domain knowledge. If you don't know anything about the data, it's reasonable to assume has a center and then it decays. So I told you, every time you think there is a center and the decay from the center, Gaussian is a good fit, even though the decay is not square exponential. But if you believe you have multiple hoops in the data, like 2 kinds of patients, for example, Gaussians may not be a good fit. Now, can I smooth the Gaussian? Suppose I do this. How can I run into trouble with this? I don't do the brute force. I fit a Gaussian. What, can you give me an example where fitting a Gaussian gives me a weird Gaussian?
Coins.
Why? Yes.
Do you have a uniform distribution? Sigma will be infinity or close enough.
So, hold on, I feed it to data, right? So the distribution might be uniform, but what I've got is 100 or 1,000 dots. So that's what I've got. I have these dots here. Can I estimate a mean with these dots? No problem. Can I estimate a sigma with these dots? Yes. No problem. So I get a Gaussian. I mean, you can say my Gaussian is no good, but I got 1, right? It's something in here. It's the best I can do with the data I have. So what kind of data will mess up my Gaussian? Will make it look bad? Okay, second trial.
It's multimodal.
If it's multimodal, so that's already I've said that. I have 2 big hoops, all the data, it's either like in reviews, everybody's either like it or hates it, and then there's nothing in the middle. My Gaussian will do something, but it's not gonna be a good estimate of the data. What else? When do I get the bad Gaussian? That actually requires smoothing. This problem of multiple hoops, I can't fix with smoothing.
Zero variance?
Zero variance. All the points are here. So if I estimate the variance, I get a 0. Can Gaussians have a variance or covariance matrix? It's a multidimensional of 0? No, because there's a sigma minus 1 in the formula. It can't sigma can't possibly be 0. So what do? I do not allow sigma equals 0. So I typically, what you should do for this beta Gaussian, I think that's also part of the problem. You do not allow variances below epsilon. So you have to be pretty abrupt about it. If something falls below epsilon, just delete it, make it epsilon, right? You have to have a line in your code. If that value is smaller than epsilon, then make the value equal epsilon. That means no variance at all times will be below this magic epsilon, which you get to set. Trial and error, you figure out what epsilon you need. You don't want to have variances or covariances with the diagonal below a certain value, because that means the Gaussian is very sharp, right? Now, the data might look like this. What's a data example where every single value is equal? Can I have such a feature in my data?
Why?
The binary feature.
I can easily have a feature where, I took all the students from Northeastern University, right? And one column of the data I have is the university. Everybody's going to have Northeastern on it, right? And then there's no variance on that column. That can easily happen in data. And then if I measure variance, I get the 0 variance. 0 variance is not a problem. Typically in machine learning, we can exclude the feature completely. If you see a 0 variance feature, just delete the feature from the data. It's not useful. But if you don't want to delete it, you want to increase the variance. Or if you do covariances, the main diagonal, you want to increase it to be always at least some value. That's going to happen in the GDA problem. Anything that do in the GDA problem, which is the first problem, you don't want you're going to have to play with that diagonal of the matrix, because otherwise you get a hard time when you compute the inverse. Okay, that's what I have to say about smoothing.
So you said that naive Bayesian network, when we use it, we get a lot of useful information about the data. So we can use it and we can get some accuracy values, blah, blah, like matrix values. But what else we can get? What kind of information we can get about data using this naive Bayesian?
So I can measure performance, right? So assuming I have a test set or a validation set, I can measure performance. If I get 90-something performance, I have a pretty good sense that I can do something per feature, right? A pretty good performance in naive Bayesian means I can judge features independently and make something out of them. Even if there is dependency, that dependency doesn't play out in the labels. I may have dependency in data, but what I'm trying to predict, the target, may not be related to this dependency. So actually, this is an important area of machine learning right now. If you have multiple targets, do you need to account for dependencies, or can you estimate the targets independently? So that's an area of a lot of papers written in the last 5 years, multi-label predictions, where people want to know, can I judge things independently, or I have to worry about dependencies? Dependencies is what complicates statistical models a lot, right? So you'd like to be able to do things independently if you can.
So the only useful information I can get is if accuracy is high, I'll say that the features are independent enough. But if it's low, then I'll say the features are very dependent.
That's not true. So it's true only one way. If the accuracy is high, you probably don't need to deal with dependencies. The target somehow is not affected by dependency if they're there. If the accuracy is low, that can be for many reasons, right? Maybe you don't have enough data. Maybe the features are terrible. Like, doesn't matter what algorithm I run, I get bad results because the features are not indicative of the target at all. Maybe there's noise. Target has been annotated by people at random. Many things today are annotated with crowdsourcing services like Amazon Mechanical Turk or Crowdflower, and in there, people who put the annotation on images, on text or whatever, they're not professionals, they're not motivated or paid accordingly, so there's easily 25–30% noise in those annotations. Okay, so if it doesn't work, you can't get a clear answer why that is.
So that's the most useful information I can get.
Is, do I have to worry about dependencies or not? All right? So that's one thing. Another thing, I want to do is there is a problem that says I have to flip a bunch of coins. Here's what I have. I have k coins, proportions by k, so then the probability, so pick a coin, flip d times, right? And then in here, I have generated, so this is at step I generate xi, which is xi1, xi2 up to xid, because I flip that coin d times. So I say run I from 1 to n. I repeat this experiment n times. Again, what do? I pick a coin. I have k coins. They have different biases. K coins with biases, Q1, Q2. What do I mean by bias?
Fair, not fair.
Probability of
Heads.
having head. So Qi or Qk is the probability of coin K to come up head. So all these coins are not fair coins. Every coin has a certain bias, aka the probability to come head. It may be 50%, 70%, 20%, 30%, so on and so forth. I pick a coin with the probability pi k. Pi k is a distribution. And I flip it d times. I get binary outcomes, right? Head, head, tail, head, 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 so on and so forth. And now the probability of a particular x will be a mixture k chosen coin is the kth one. That's the mixture we've seen for EM before. Because this is a standard experiment that says you pick a coin with the probability pi k, and then you flip that coin. And you flip a coin, you follow the distribution of that coin. The chance of seeing a particular sequence of head, 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 tail, tail, head, head, right? So this could be head, head, tail, tail, head, tail, head. That particular sequence, probability of seeing that sequence, it's the probability just for that coin to see that sequence. Make sense? So this is the same as the EM algorithm. When I have k distributions to generate data, those are the coins. Depending what coin you pick, you're likely to see different frequencies. If a coin has a high bias, I'm likely to see many heads. If a coin has a low bias, I'm likely to see less heads. What's the expected number of heads I'm going to see? Just as an exercise. If I pick the coin k, what's the expected number of heads in d tosses?
Qk by d.
How much?
Qk by d.
Qk times d. Right? It's a linearity of expectation formula. If I flip it once, what's the expectation of a head? Qk. But I flip it d times, and the number of heads is an addition of this head plus that head, whether it's 0, 1, 0, 1, 0, 1, I get d times qk. Okay? So the problem is giving you this data, this X matrix. It says, I've got those flips, n trials, d times each coin. You know that there's the same coin being flipped in a row, because the coin has been picked for the row and flipped d times. You get this data, and what we're trying to do? Find who? Just like in the last time, what did we try to find? The model parameters, which are who? The QKs, the biases, and the
IKs.
IKs. That's this problem. Now, there is a note here that gives you the update formulas, right? It tells you, you do EM. How are you going to do EM? E step is going to be? Well, there's another thing that's a hidden variable here, right? which is the same as before. Let me do that before that. Who's Zik here? Remember who Zik was in the EM problem? I have those patients, 3 Gaussians. Who was Zik? It's a random variable. So I don't know its exact value, but this is 1 if and only if what?
Data point is in K class.
The point xi,
Is in K class.
which was xi1, xi2, the whole vector, was obtained
By a flip of point K.
by flipping point K. Now, I'm never going to know that for sure. Any coin can generate any sequence, right? I mean, assuming I don't have 0 bias or 1 bias. Any particular sequence, H, HT, HT, H, could have been generated by any coin in my data. Depends up who's with me. Okay? Well, this is the effective core of the whole generative process. You gotta understand the setup. I know I've said this 3 times. I'm gonna say it one more time. We get lost into probabilities and matrices, calculation, all that, which is not essential because you can do that later if you need to. Essential is to understand the setup. And if you lose the setup these past 2 weeks or the next week when you work on the homework, we wasted our time in here. Okay? So you gotta understand the setup. Zik, it's a hidden variable that's neither given to us nor we need to compute it. We don't need it at the end, the Zik. The model parameters do not include Zik. So in many processes, it's called a hidden variable because we need to make use of it internally, or we are going to make use of it, but it's not explicit, right? In these generative processes, we know that the coin has been picked. There is a coin that flipped the xi row. But in the processes last time, we assume that's the model, but we don't know in data that for sure there was a Gaussian who did the flipping for us. It's not the case, right? Patients may have come from some sources with some diseases. We don't know if they generated by Gaussian. In here we know for sure that the setup tells us that coin is the coin that been picked and the same coin has been flipped 10 times. So the Zik is this indicator which coin corresponds to which row, right? Which we don't know. And very importantly here, any coin could have generated that sequence. But now the same probability, right? If I say the sequence is H, 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 tel, H, 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 can a coin with 10% bias, 10% chance of heads generate this sequence?
Yeah.
Yes.
Yeah, in theory. But what's the chance for that to happen? Pretty small, right? So it's true that every coin can generate the data point, just like I show you that picture with 3 Gaussians and I pick a point X and I say, what's the chance to come from the first one? It's very, very small. What's the chance to come from the second one? That's much higher. What's the chance to come from the third one? You know? So any Gaussian could have generated that data point, but some of them are much more likely. The same thing happens here. So now who's the E step? What we're gonna work with is Zik, which is on all those mixture models, is the probability of Zik equal 1 given xi. That's also the expected value of Zik. Because you should know this. Random 0, 1 variables, their expected value is the probability of being 1. Think about expectation. It's 1 and 0, 2 possibilities. 1 times probability 1 plus 0 times the probability of 0. So how much is that? Probability of 1, right? Any 0, 1 variable, its expected value is the probability of being 1. So the probability of being 1 is its expected value. Now E step. E step is doing what? Is recomputing Zik given pi k and QK in this case. The parameters I have for these distributions are going to be those. This is the same like before. Of course, it's going to be a different distribution. P of x, I'm going to get to that in a second. This is not the Gaussian distribution, right? When you flip coins, you don't get the Gaussian distribution. But the formula for updating ZIK in terms of those probabilities will be the same. Can we remember that formula first? Is probability of x given the coin k times pi k normalized. Is that true? That's how it was? So that's the same formula except the p is not a Gaussian function here. What about m step? It's recompute who? Qk and pi k given memberships probabilities, right? ZIK. This is the membership, which is a soft membership because it's a probabilistic one. There was a question? Yes.
Before starting each step, after I do this experiment, like I flip n coins d times, will I have the value of pi k or qk?
No, it's the same like before. You're getting the data matrix x, you see the observations, you have to compute the coefficients, which are pi k and qk. That's what the problem's asking.
Oh, got it. But how is it that it is given? So here, evaluating.
So we have to start with something. Like
Just randomly.
in k-means, right? We're given a bunch of points. We have to compute the clustering. That means centroids and what else, but we're not given initial centroids. We got to find them. So there is an initialization step of EM, which is non-trivial. You guys are gonna have to play over the spring break, I'm sure, with this EM to make sure to see what happens. It's true. You got to start from somewhere to do those steps, right? You have to either find the ZIKs, the memberships, or find the pi k's and qk's somehow to start from somewhere. The E step is the same, just different function. How about the M step? I say pi k is the same. Remember who pi k was? The size of the cluster? So who's that?
The probability of picking.
Remember who that was? That was the size of the soft cluster. So was the sum over
For all I and
all I.
probability of xi given that you chose k.
Was like this, right? Xi times the ZIK, which was the probability of coming from that k. And then it's a sum over sum of ZIK in here. In here, I'm going to point out, I don't want to solve the problem for you. My intention here is for you guys to understand EM well enough on the Gaussian mixtures, so you can come here and make sense of what those formulas are. The derivations are not required, they're given to you. So if you don't want to bother with it, but you should bother with it, but if you don't want it, just implement the formulas, run EM, you're going to get some answer, that's the one. Now, people who want to bother with it should try to derive those formulas. So in this formula, in this paper, there are two differences from before. So that's my first question for people who want to study this problem. This is not xi. This is size of xi. By size, I mean how many heads are there. So size of xi. Xi is a sequence, is the number of heads. So this sequence, how many heads are here? 4. This sequence? 7. It turns out that for modeling coin problems, it doesn't matter the order. As far as the coin bias goes, suppose I have a bias of 70% or 60% or 20%. Any sequence that has the same number of heads will have the same probability. So this sequence versus H, H, T, 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 H, H, right? Or T, T, H, 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 H. these sequences have the same probability for a particular coin. So the order we can skip. The order of the heads tails doesn't matter. What really matters in this case, the outcome that we care about is not the sequence. It's just how many heads are there. Yes.
Is that because the coin flips are dependent on each other?
Yes. The number of heads, well, there's a chance of a head at one flip, and then that distributes over the whole D sequence, right? So there's one thing that's the size of Xi, number of heads, and the other thing that I would like somebody to explain to me, there is a D here in the bottom. So for D equal 1 is that every coin I choose is flipped once, but for D equal 2 or 3 or 4, there's a D in here. So that's, again, when you judge this update formula, you should look at the EM one and say, okay, how does this correspond to the EM formula? What's the difference here? And the hardest part will be this QK. Yes?
Can you repeat what D means?
Who?
D.
This D? That's the number of flips I do for each coin. So if I do 10 flips, this is a fixed value that's known in advance. Every coin has been flipped. Because you see the data matrix, so you see the number of columns in there. There's D columns. There's a D in here. It has to do with using this outcome, not Xi, but the outcome that matters for us is the number of heads. It doesn't matter the exact sequence. What matters is how many heads are in there. That's going to make the difference between the biases. The other thing is, oh wait. The other thing is this QK. Now, I need something to compute this QK. Something I didn't do yet. It's not a Gaussian distribution, right? So what is it? Right? I need to do something. What is the probability? This is Xi, the sequence. What is the probability of seeing this sequence given coin K? Yes.
The probability, the bias of K.
That's QK.
QK raised to D into 1 minus.
What is it? Somebody said the name binomial. What is it? Binomial. Then. Yes.
It's D choose number of heads.
D choose.
Number of heads.
That's the size of X, number of heads, right? Okay.
Times QK, the side of X. Times 1 minus QK to the D minus side of X.
Like that? I don't know. If you remember these coin problems from undergraduate years, yeah, binomial distributions. So what happens if D is 1? Just verify, quick verification. D is 1, what do I get? This is going to be 1. So if D equal 1, what this probability becomes? QK at size of X. Size of X is what in here?
That is 0.
Whether it's head or tail, because there's only one, so it's head or tail. And 1 minus QK at D minus X, well, that's 1 minus X. So that's, if it's a head, the probability of seeing the head is QK. That's correct. And if it's a tail, the probability of seeing a tail is 1 minus QK. Right?
That's it.
Okay. So I'm going to need to take this function, differentiate it, to get the QK out. I need a likelihood function. Because this is for 1x, and it's for only one coin. So what's the likelihood? Is the product over all data points, right? Always the likelihood is a product over all the data points. From the probability of that seeing that point, right? That the probability of seeing that point is the product, is the sum here over K by K E of x given k, zik equal 1. Maybe I can write this in a more fancy ways, but I need a log in here. So that's going to be a log of this. And I need to use the EM derivations that we've seen last time, but now the Gaussian function. Last time we see the differentials for the Gaussians. In here we have to differentiate this. It's not hard. So I'm not going to do that in class. But in this paper here, there's a reference. That reference contains the derivation. It's only 4 lines. So that's part of the homework. I'm willing to discuss this at office hours, but only with the ones who want to see the math or went through the math and don't understand it. I would say this is actually easier than the Gaussian, because you don't have to deal with that sigma differential. In here, I think it's just unidimensional binomial functions, not too bad. Especially if you've seen this distribution before, I think it should be fine. So let me connect my projector before Kitchen comes here, and show you some things. Is the derivation. We can go over it a little bit over it. So what happens here? Not the whole thing. This is the probability we've been talking about. That's the mixture. And in this derivation, the function p. Do we have it here? Is here. That's the Bernoulli with d equal 1, right? This is flipping it once. You either get qk heads or minus qk tails. Now the problem you have is with d, so you get the binomial distribution with the binomial coefficient with the d. So even if you read this derivation, you gotta change it for d flips instead of 1 flip. But I don't think that's that hard. So then what do we have? We have to do EM. So that's the theory of EM here. We can skip that. Here's the mixture. Here's the likelihood, right? So how do they define this likelihood? The product of n equal 1 to n, that's what we've seen. It's all the data points. Why there's a product here of k equal 1 to k of that? So the sum I have with the mixture distribution, right? I put in there a sum. That says an expectation. That's the probability of seeing an X across all possible coins or all possible hospitals if I have patients. This one says, if you know the value of Z and K, that's a discussion we had Tuesday at the end of the lecture. If I know this value 0, 1 exact, I don't have to worry about the mixture as a sum. Right? Because I know which component of the mixture generated this X. Of course, I don't know that. I can't really use this. But instead of using that sum in here, you realize that this product only has one term in it. The second product, it's only something for Z and for the K that has Z and K equal 1. Because all the other components have power 0, so they don't matter. Who's with me in here? Hands up. Let's try this again. Everybody understands this is over all the data points. Now, the product, this product is not really a product, it's a selector that says choose the component that generated that xi, because only the component that has z and k equals 1 will count. Everything else will have z and k equals 0, so it will be something at power 0 equal 1, right? That's what's going on. But they write it as a product to have a generic form. So this, of course, is possible if I know which z and k is 1 and which z and k is 0. But I don't know that. I can't use that. That's the discussion we had at the end on Tuesday when I say you can't really maximize this likelihood. You have to take expectations to not have z and k in there, or zik, how I call it, to have instead expected values of zik. So that's the same thing that happens here. The likelihood, the actual likelihood is this, but this is impossible to optimize. Remember that discussion when I say we actually optimizing the lower bound, and the lower bound is the expected likelihood over the values of zik, because we can't deal with zik in an explicit form like that. So the only difference in this paper is that instead of my zik in these brackets that I have, right? I call this zik, the probability of zik equal 1. They call it gamma of zik. So this gamma of zik is my notation for this is probability of zik equal 1 given xi. They call it gamma of zik. So then what happened from this likelihood to this likelihood? They take this expectation. Instead of having zik written this way, they say we can't maximize that, so we're going to maximize this instead, which we can prove, like we did last time with that Q function, that this is a lower bound. So by optimizing the lower bound, we have at least a sense that we found the maximum on an actual likelihood. But it's no guarantee, right? So that's what's being there. So far I think everybody can follow, no problem. Now in here, we have to take differentials. They actually skip the differential. They say, differentiate this, you get that. But let's try to take the differential in words, so to speak. No math on the board, right? What happens if I take the differential with respect to qk in this function? The sum stays, right? How about this sum? Only that k stays. The other k's that don't have qk is them, they're gone, right? So in here, this is a constant. Whatever this is that's dependent on qk, that's going to stay. Log of pi k, that's a constant, so that goes away. If I differentiate x times log of qk with respect to qk, what do I get? X by qk. If I differentiate y minus x log of 1 minus qk with respect to qk, what do I get? We have to work that out, right? So log of something is 1 over that something, but I need to differentiate this part inside the log, that gives me a minus, and I still have the 1 minus xn is a constant in here, it just goes in front. So I'm going to end up with a sum of n, right? This remains, the log pi k is gone because that's not dependent on qk. So I have this times xi times 1 over q plus 1 minus x times log of 1 over 1 minus q. I have to work out that algebra. I have it written here, 3 lines to get to this qk. So the job for you guys is to say, okay, that's for a binomial, for a Bernoulli distribution, because d is 1 in here. Now, I have flipped that coin d times. So what did I say? It's not this xi here, it's the outcome, which is, if I flip it only one time, x is the number of heads. It's either 1 or 0. But if I flip it d times, the size of x now can be any number between 0 and d. Okay? There's another thing I want to show you, but I'm eating into kitchen's time here. Another thing that I want to show you is something from a book that's recommended for this class, but not mandatory. That is this Bishop book. Extremely good machine learning book, but too advanced in statistics to read it at 6140. The reason that's not it's mandatory for this class. I think some other sections over the years use that book, but it's too statistical for our background in statistics. But if you could read that book, that's very good. There is this chapter 8 in the book, which is Introduction to Graphical Models. That is when we know we can model all dependencies at once like we do GDA in data. That's not going to work. So we want to break it into dependency parts. But on the other hand, we don't want to break everything independently like naive Bayes does. So we want to keep some features dependent and some independent. So how do I look at the dependency network? I have all these variables, those are my features. How do I determine which ones are dependent and which ones are not dependent to break it? That's what's in this slide. So I'm gonna skip around. This is a little bit of an introduction, how to think of random variables. So one important concept about random variables that's in here is the notation here, it's every time you see something filled up, that's a known thing. So this is an unknown thing. It's still a random variable. It has a probability of being red, blue, green, or whatever. This is a known thing. So conditionals work very differently when you start knowing values, right? Once I know something, depending on the value of this random variable, I can make different instances for the others. So this is an introduction. One thing that that you want to know here, I'm going to skip a few slides, is this independence notion. So this this sign of perpendicular with the double vertical bar means independence, given something. So what this one says in here is that A and B in here are not independent, because there is a dependency from C to both of them. In other words, C influences both of them. So because C influences both of them, they're not dependent. But if you know C, they become independent. So whatever values you observe in a certain C class, I already know I'm talking about all the students who take 6140, for example. Then if you have this kind of dependency and no other arrow between A and B, then A and B now are independent. I think that would be a very useful exercise for people who want to go into more statistical machine learning, to go through some of this stuff. You may have to read more than chapter 8 to get here. And towards the end, so there's more examples, and towards the end, it's the purpose of this ultimately is to take a graphical models. So in the graphical models, you have to specify the dependencies. You have to somehow estimate which variables are dependent and which ones are not. So that may come a lot from domain knowledge, or it may come from correlation, right? If I compute the covariance of a matrix, I look at the values that are not on diagonal, I know which ones are dependent. So in here, I have, say, x1, x2, x3 independent, and they all depend. They have dependence to x4. In here, I have everybody dependent to everybody. A graph that's complete independence, it's hard to deal with. There's just too many dependencies. So in practice, people would, if you want to use a graphical model, you have to restrict those dependencies to sizes that you can deal with. So what's the plan here? The plan in general is to factorize the dependency graph. So what this is saying, if you given a dependency, somebody gives you a dependency graph between the features, those are the variables, right, the features. You want to create these factor nodes that determine who's dependent with who. The factor nodes are independent of each other, but each factor node creates a dependency, expresses the dependency between a few variables. Once we manage to do this, if we manage to do this, we can treat the factor nodes more or less independent. That's easy, right? We break the network into independent parts and we estimate this independently. And then inside each factor node, we have to deal with that dependency inside there. So inside the factor node, maybe like a modeling, something like GDA or brute force or something. But among the factor nodes, we can do independence inference. The difficulty is how to break the network into factorization. So the rest of the slides, how do you take a given graphical model, which is a graph with dependency between variables and factorize it so you know which parts are independent and which parts are dependent. And you want the factors to be relatively small. If I get a factor of only 3 variables, I can deal with this dependency somehow. But as soon as a factor becomes very complex, it means, again, I'm back to the problem where there's too much dependencies to deal with, and I can't measure it. And they give in here a basic algorithm. It's called, I think, some product, how to make inferences. It's based on marginalization into very specific graphs. Those are not general graphs. There are papers written into how to take simple graphs first and run inference, and then this can be done. This is reasonably easy to do. It could be a class project, for example. One of you could do a class project into how to do inference in a network that's simple, aka say a tree or a DAG. A DAG, you know, doesn't have cycles, right? But then there are fancy academic papers that take a general graph. I think it's called the junction tree algorithm. You take a general graph and you transform it into a DAG first to do inference in the DAG. So inference in a general Bayesian network is difficult, but if you transform the network first into a few steps, then we can run these models. We did the extremes. We did model all dependencies with a simple function that was Gaussian, or model no dependencies by doing naive Bayes and independent each feature. This is in the middle. It says, first break the network into some dependencies, and then the independent parts you can deal with independently, but each dependent part you have to deal with it specifically for that dependence. So this would be the next step if you follow this Bayesian track.
So is it like that factorization is just different feature that we add?
No, factorization, you take the graph and you run factorization on it. There's an algorithm that factorizes the graph for you. But it doesn't work well on general graphs. It typically works well on each factor becomes small. So the dependencies are 2 or 3 variables. In fact, a lot of machine learning algorithms that deal with dependencies and are used in practice, the most popular is called CRF, conditional random fields, only deal with dependencies between 2 variables at a time. So it models all dependencies that can be expressed as a combination of 2 dependencies. It doesn't deal with higher level dependencies, 3 or more variables being dependent. And now Ketchen, can we still do a demo of something? So Ketchen is at homework 4, a little bit ahead of you, and he will show you some stuff in 8 minutes and maybe some stuff on Tuesday, the remaining one. What kind of jack you have there? HDMI? Yeah. Don't go fast. Do what you can and we'll do the rest some other time.
Okay, so I'm going to show you the code and some implementation details and the running results. So in homework 4, we need to implement some generative models. So first you need to try the GDA and naive Bayes on the span-based dataset. So now let's try one. So first we run GDA with one covariance matrix. You can, so here in the homework we say you can pick either one covariance matrix or two separate covariance matrices. Either one is fine. And you can see here we have 10 force. We do cross validation here, and the first one is GDA with one covariance matrix, and the second one is with 2 separate matrices, and we can plot the ROC curve here. And for naive Bayes, we need you to implement 4 different versions with different assumptions. First one is you need to assume
Hold on. You have the GDA code?
Yeah.
Can we see it? We need to see it bigger.
I mean, after I introduce these results.
Okay.
Yeah. So, right, let's see the code. Actually, you can see the training is very fast because for this kind of model, we don't need to do it so many iterations or so many epochs. We just need, for example, for the GDA model, we just need to implement two functions. One is for training, the other is for the prediction. So in training, you just need to summarize you feed in the data set and you need to summarize the information to estimate say the prior or the mean or covariance. So you don't need to train it so many epochs. So this is very fast. And during prediction, you need to make a prediction based on your estimated parameters, your estimated models. So yeah, this is for GDA. And for the implementation, when you calculate the covariance or average, you can either implement it manually or you can call some like scalar functions or scipy functions. Either is fine. So for naive phase, you need to implement 4 different versions with different assumptions here. Based on my running results, you can see the first one. If you assume a Bernoulli, multivariate Bernoulli distribution, then you will get the best performance here. The average accuracy is around 0.9. Let's look at the code. So this is similar to the GDA implementation. You just need to implement a train function and a predict function. So in the train function, similarly, you just summarize the information based on the input data set. But one thing you need to do is, as Virgil mentioned in class, you need to do the Laplace smoothing. For example, if you assume a Bernoulli distribution, you need to do some smoothing like this. And similarly, for the Gaussian distribution, you also need to do the smoothing for the variance when you calculate the variance. So that's GDA and naive base. Any questions? Then you need to implement the EM algorithm, which is the Gaussian mixture model. So first, we provide you with two very simple data set. This is our simulation data. So first, you can assume there are only 2 clusters. This is 2 Gaussian. So if we look at the data generator, we can see for class 1 we have 2,000 data points, and for the second clusters we have 4,000 data points. And these are our the mean and covariance of these two distributions. And then now we need to implement a model to fit this data set and estimate the parameters of the mixture model. So now let's run it. So as the training going, you can see those estimated parameters are getting close to our predefined parameters here. So at the end, we can see here. Yeah. So this is the output of this is the final estimated parameters. We can see for the prior, this is 1/3 versus 2/3. So this is similar to what we predefined here. And you can see the means and covariance, the estimated values is basically the same as what we predefined here. And if we plot, we can show the estimated distributions and the original data set here. So this is at the time step 0. So at the beginning, we just randomly initialize the parameters in our model. So we can see our two distributions cannot fit the dataset very well. So how to check this? We can check if we project the mean of the distribution to the ground. We can see whether we need to check whether this is the same as the mean of the dataset. If you compare the time step 0 with time step, the last time step, we can see these are two very perfect distributions. These two distributions can fit our dataset very well. You don't have to plot these things, but if you do this, it's better to, it can help you to train your model or better understand your model. Or also, it's helpful for you to debug. So, similarly, we have the data generator for the three Gaussian distributions. So we predefine some parameters here, and if you run the Gaussian model on this data set, yeah, at the end you will get some similar result. The estimated value of the parameters are similar to what you predefined here. Any questions?
What function do you use to get that 3D histogram or the 3D Gaussian distribution?
The EF algorithm?
Yeah, just like what library, what plot function did you use?
How do you plot it?
How did you plot it?
The matplotlib.
Like plot 3D or plot Gaussian or something?
Yep. The highlight also.
Oh, what is it?
Axis 3D.
Okay, thank you.
Yeah. Any other questions?
Well, let's stop here, and if we need to do the coin, we'll do it next week. No, we'll stop here and maybe we do the coin next week.